Vaughan did a PhD at the University of Geneva in 1979. Afterwards, he spent a few years at UCLA and 10 before arriving at UC Berkeley in 1985. He took a job at Vanderbilt in 2011 as the Stevenson Distinguished Professor. Some of his major results include the classification of outer actions of finite groups on the hyperfinite 2-1 factor, the Jones index rigidity theorem, and the discovery of the Jones polynomial. He has numerous accolades. I'll just hit the high points. He received the Fields Medal in 1990, and he is a Knight Companion of the New Zealand Order of Merit. And it's great to have him here.
But so show a bit of solidarity for with the local team here. Well, thank you all for coming out. I realize, it's middle of the semester and there's lots going on, so it takes a singular effort to come to these talks. So I'll try to make it worth your while. I'm going to give 3 talks, and the first one, sort of unusually for this kind of series, the first one will be completely disjoint from the second and the third. So if you don't understand anything today, you can come along and not understand anything again the next couple of talks. So before I get started, so in the title of this talk is the terms Phenomen Dimension, and hopefully you'll be leaving this room with some idea of what that is. But I'd like to acknowledge, before I even start, my debt to a couple of other mathematicians in this work. The first one is a quasi-local here. I think he's Alain Cohn. And you can't really do Phenomen algebras without being strongly influenced and having received a great wisdom from him. And this point of view that I'm going to put out on the Phenomen Dimension is something that I somehow inherited, along with other things, from Alain. And the other person who's perhaps less well known is Florine Radulescu. And I will cite explicitly some of his results, which have been very significant for me in this work, and you'll see how they fit in the course of the talk. All right, so sadly I have to admit that I'm not a young person anymore, and as I've got older, I've interests changed, and I've become a little bit less interested in the internal structure of Phenomen algebras, which motivated me a lot when I was younger, and is where I I think made my main contributions. But I've remained interested in Phenomen algebra more in how they interact with the rest of mathematics, and in particular, sort of an even narrower field of results in mathematics that are very simple to state, have nothing to do with Phenomen algebras, but for which the best proof, and perhaps even the only proof, is by a fairly simple detour through Phenomen algebras. There's not too many of these, but I hope to add to that list today. Let me tell you my all-time favorite, which is a very simple result. I think it's due to Kaplansky, but if you asked Kaplansky, he would have said, well, von Neumann knew about it. And it's the following. So if you have a group, gamma, so that's a group, and a field, F, then you can form the group algebra F of gamma, which is the set of all linear combinations where gamma is in gamma. And there's finitely many of those are non-zero. Okay, so these are just formal linear combinations of group elements, and then you multiply them according to the group law, which is extended by linearity in the obvious way. So you just turn the group into an algebra. So this is the group algebra. And the result is the following, that if the characteristic of f is not 0, sorry, the result is that if the characteristic of f is 0, then AB equals 1, if and only if BA equals 1. Okay? There's an extremely simple proof via Phenomen algebras of this result, which I'm not going to give, but it's just because of time. It's easy to give, and after I've done what I've done, if anyone's interested, I can actually give you the proof. But it's sort of, apart from some simple modifications, it's sort of the only proof around, as witnessed by the fact that, as far as I know, the problem remains open if the characteristic is not 0. Okay? You get the characteristic 0 result by embedding the field in the complex numbers, or the relevant part of the field in the complex numbers, and thereby getting into Phenomen algebras. Now, I'm not assuming that you know what Phenomen algebras are, and hopefully you have some idea of that when you leave this room also. Okay, so in this lecture, I want to give 3.5 results, which fall into this category of results that are very simple to state, that have a proof by Phenomen algebras which is very, very simple, but from what I can tell at the moment, no other proof, and I will argue that in one case, any other proof is going to be extremely hard. The results, as I said, don't involve Phenomen algebras, so you don't need to know anything about them to understand what I'm saying. On the other hand, they are about something, so I have to tell you a little bit about the something that they are about. So there's two different but related areas that these results are going to be stated in terms of. And basically, the first one has to do with complex function theory, and in particular, the theory of Bergman spaces. So it's very confusing in this area that there's the Bergman spaces and then there's the Bargman spaces. And one of them uses one n and the other one uses two n's, I believe. And I think I've got it right. This is Bergman uses just one n. So these are very simple function spaces. They have, let me define the ones that are going to be of interest to me. There's a bigger family, of course, as there always is. But the ones that I'm going to be after are typically written A, P of alpha. That's what they are, AP of alpha. No, so this is the set of all F's from, we have two friends, the upper half plane and the disk, unit disk, which are, of course, equivalent under the Cayley thing, z minus I over z plus I. So you can always phrase everything in terms of one or the other, whichever is more convenient. We're going to do that. So they're functions from these two spaces to the complex numbers. They're holomorphic. And they are, the 2 refers to some kind of Hilbert space structure, and that is the p equals 2 refers to the Hilbert space structure, so they are square integrable with respect to a certain measure, which I'm going to do maybe in the disk. No, I think it's easier to write down in the upper half plane. So here it is. So it's the integral over the upper half plane. Now the upper half plane is z, which is x plus iy. So there's two real coordinates, x and y. And we want the integral of absolute value of f of z squared times y to the alpha dx dy to be finite. So the L2 functions, which are holomorphic, and you remember from complex analysis course that if you have a L2 limit of holomorphic functions, the limit is necessarily also holomorphic by some version of the Cauchy integral formula. Okay, so that's what your Bergman space is. This is the L2 Bergman space. Obviously, there's LP ones. Everything I say is going to be to do with L2, and I don't know if these techniques would extend at all to LP. All right, now. Right, thank you, Henry. That's exactly what I was going to come to. We all know that the SL2R, well, strictly speaking, PSL2R, but I'm going to fly way above the difference between PSL2R and SL2R, so don't complain. This acts on H or D by linear fractional transformations. I guess it's called SU11 if it's acting on the disk. And that action preserves the hyperbolic measure, which is dx dy over y squared. Which is why when you run into these spaces, these Bergman spaces, you often see instead of A2 alpha, you have the parameter alpha, you have A2 S minus 2. So I'm going to call S this version of the parameter where the measure that we're looking at, is y to the S minus 2 dx dy. You can see how the two differences in schools arose. This is just sort of Lebesgue measure modified by something, whereas this one is hyperbolic measure modified by something. So they both have reasons to exist. So that is, I think, just about all I need to say about Bergman space in order to define. Right, this is actually, that number S or alpha is actually the weighted Bergman space. Right, so I do want to say just a little bit more at this stage. I probably don't need it to get to the result, but state the result. But let me tell you anyway. So SL2R acts on H, and it doesn't preserve the measure, okay? Because it preserves hyperbolic measure, but not the other one. So therefore, it's not going to act just in the trivial way on the L2 space. However, what you can do is you can fix the action by some kind of co-cycle so that it actually does act. Now, since in your measure theory course, you take the Radó-Lectures derivative of the transport of the measure, take a square root and multiply or divide by that. But here you want to preserve holomorphic functions, so it's very important that when you modify it to preserve the measure, to become unitary, that you do it with a holomorphic function. So here's to sum up what I'm saying is that there is a unitary representation of the group SL2R, so gamma is an SL2R. Actually, why not? Let's call it ABCD. There it is, determinant 1. So we define U gamma of F of Z. F is one of these L2, this is a guy in Bergman space. A2L, let me use S. Then this is 1 over CZ plus D to the S F of AZ plus B. Actually, this is, you always have to fiddle with the, okay, so this turns out to be the right thing to multiply, to change everything by, to make this a unitary transformation. Remember, if we'd been looking at hyperbolic space with this measure, we wouldn't have had to have any such factor, but we wouldn't have had too many holomorphic functions. In this case, when S is bigger than 1, we have lots of holomorphic functions, and this function here, this denominator has no zeros, so it has no zeros, so no poles. So this is a holomorphic function, provided you choose, there's some choice of holomorphic square root of S squared. S is a real number, notice. S is a real number. So there's a little bit of fiddling, which I'm also going to try to fly above what the meaning is of CZ plus D to the S. Okay, but anyway, so we get this unitary representation of SL2R on the Bergman space. So SL2R acts on A to S alpha unitarily. Okay, so that's pretty easy stuff. So that's all I want to say now about Bergman space. So the other ingredient is going to be the theory of cusp forms. So cusp forms. So both of these topics that I'm explaining to you are probably known very well to certain subsets of the audience, but possibly they're largely disjoint subsets. So let me just tell you exactly what a cusp form is. First of all, it has in common with a Bergman space function in that it's a holomorphic function on the upper half plane with values in the complex numbers. And the most important, the primary thing that it has to do with this action of SL2R, but in fact I'm going to restrict to, just for simplicity, I'm going to restrict to the subgroup SL2Z of SL2R, which I'm going to call gamma if I ever need to abbreviate it. That's equal to. Everything I say has extensions to arbitrary Fuchsian groups, which are other discrete subgroups of SL2R. So when I say cusp form, I mean cusp form with respect to this particular group. And its primary thing that it's got going for it is this sort of equivariance under SL2Z, which of course is going to be reminiscent of this way of fixing up this representation. If you transform a function by this linear fractional transformation here, and this factor here, this sort of fudge factor with the p, it's not, the function is not actually invariant, but it's invariant up to this factor, then that's step one on the way to being a cusp form. This is the modular condition, and if you just satisfy these two, you're probably called a weakly modular function or something, because you satisfy the algebra but not the analysis. All right, so this number here is supposed to be an integer, and it's the weight of f. So cusp forms have weights, and that weight is the scale factor by which this transformation goes. Okay? So that's ultimately the most important thing. The next thing that they have, I need to describe, I need to take one particular transformation, which is the matrix 1, 1, 0, 1. And if we apply that, C is 0 and D is 1. So this says f of z plus 1 is equal to f of z. So it's periodic if we add into the real part of z. So this means, this immediately implies, think about it for half a minute, that f is a function of e to the 2 pi I z, which we're going to call q. Okay, so we can talk about f of q rather than f of z. And what makes this function a cusp form is holomorphic, so we expect it to have a Taylor series or a Laurent series expansion about any point. And what makes it a cusp form is that f of q has the following: a1q plus a2q squared plus a3q cubed. So when we write it out in a power series of q, which has to exist somehow because of holomorphicity, then there's no negative powers of Q, and there's not even any constant term. It starts with Q. So let's think about the upper half plane for a second and see what happens when the imaginary part of Z tends to infinity. So if we're going up here, then e to the 2 pi I z is e to the minus some real part, which is going to infinity. So this tends to 0. Q tends to 0 rapidly. So these cusp forms are chosen among the modular forms, modular functions, by the fact that you have rapid decrease at infinity of the function in the variable Q. Okay? So that's a cusp form for SL2Z. Well, these things are the stuff of analytic number theory. Are there any questions? And the results that I'm going to state involve them. But just to say a little bit more, let me give you an example. They're all known, these cusp forms. They're completely understood. They form an algebra. When you multiply two cusp forms, you get another cusp form. All that happens is you add the weights. If you add the weights, and then obviously if you multiply two of things like this, then you're going to certainly get a zero constant term. In fact, they're going to get even higher and higher powers of Q as you multiply them. So they form an algebra. That algebra is completely understood. And there's one particular element, which is the smallest element that you ever see, and it's called delta. And it's also called the modular invariant. Modular discriminant. Crops up in elliptic functions, of course, and their relationship with cubics. So here it is. I'm actually going to write it down for you completely explicitly. It starts with Q, but it's easy to remember as a product formula. So it's 1 minus Q, 1 minus Q squared, 1 minus Q cubed. And all of that part is raised to the 24th power. Okay? So you can check, actually you probably can't check, but you can look it up in a book, that this is obviously invariant under this transformation, z plus 1, z going to z plus 1, just because it's a function of Q. But you can check that the other transformation, which is 0, 1, minus 1, 0, together these generate SL2Z, that it's also invariant under this one with the appropriate CZ plus D factor. Okay? So that's the famous function. And just in passing, in case you didn't know this, you can write it out, as I said, as in terms of as a power series explicitly. And any high school person could do this, right? All you got to do is use a binomial expansion to raise everything to the 24th power and then multiply them out. You can write this out, and you call the coefficients t tau of 1q plus tau of 2q squared plus tau of 3q cubed plus dot, 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 dot. This function of tau that you get is called the Ramanujan tau function. It's got all kinds of wonderful arithmetic properties, and it's an open problem as to whether it is non-zero for every n. Right? Is tau of n non-zero? Well, you can just go ahead and start expanding it and see if it's non-zero, and you'll find that it always seems to be. Okay, so I think. Oh, one other thing about the cusp forms before I go on. Oh, did I say what the weight of this was? This is weight 12. So this P here is 12. And that's the smallest weight you can get. There's no cusp forms of weight 2, 4, or 6. This weight 12 is the first one. There's a wonderful book, actually, where you can read about these things. Cusp forms, anyway. by Sayre, and it's called A Course in Arithmetic. And it's a very good book to leave around if you're having a party for non-math people, because they sort of see this book and they say, oh, A Course in Arithmetic, I can do that. And see the reaction. I'm sure that's the joke that Sayre intended. All right, so there's one other thing before I state my 3.5 theorems. And that is this, you can take, if you take two cusp forms F and G, and then you take F bar times G, and you take it y to the p, oops, y to the p, not minus p. Anyway, this thing here actually ends up being, probably with a 2, being actually strictly invariant under the transformations in SL2Z. So you have the transformation of this one and this one and this one. They all combine, I think this is right, to cancel. And this thing is invariant, totally invariant under SL2Z. It's not holomorphic. That would be not fair. But so you can integrate it over any fundamental domain you like. So remember that for the action of SL2Z on the upper half plane, we all know that there's a fundamental domain we'll have over here, which is this picture here. F, this is the real axis here. This is I. This is e to the I pi over 3. This is e to the 2 pi I over 3. And this is the fundamental domain. This is minus a half, plus a half. And what that means is that this area, this region is transported when you look at the action of SL2Z on the upper half plane. This goes disjoint to itself all over the place and forms this tessellation, this paving of the upper half plane in a very nice way. So you could integrate, if we call that F, we could integrate over F of this times dx dy over y squared. That's an invariant measure. And that will not depend on the fundamental domain. So I could choose another fundamental domain and I'd get the same answer. Okay, so this is obviously a number of considerable interest. You can check that it's actually, that these integral converges. And this is the FG, this is the Peterson inner product. Over cusp forms, and that's of some interest to number theorists for various reasons. It's obviously positive definite. It's positive, obviously, and definite because of these things are holomorphic. So if it's 0 on the fundamental domain, it's 0 everywhere. Right. I think I've introduced everything now. So let me just quickly recap the things that we've seen. We've seen these Bergman spaces, and we've seen cusp forms. We've seen an example of a cusp form, and we've seen this Peterson inner product of cusp forms. All right, now I'm going to state these 3.5 theorems. So let's do theorem 1. And actually, this will only involve the Bergman space. This won't even have the cusp forms in it. So here it is. So if S is greater than 13, greater than or equal to 13, there exists an element of Bergman space, A2, S minus 2. So I have my prejudice to be using the invariant measure in the upper half plane. There exists an L2 function such that if you take gamma belonging to SL2Z, so for all gamma in SL2Z, the inner product of U gamma xi is equal to 0, except so this function has this bizarre property of like a fundamental domain. A fundamental domain gets sent disjoint to itself by the group. This function gets sent orthogonal to itself by the group. Okay, so that's the theorem. The second theorem is somehow complementary to this. Actually, I should say this is an if and only if. This is not very good grammar, right? But this property is equivalent to S being greater than or equal to 13. Okay? Now, if we want one for greater than or equal to 13, we better have one for less than or equal to 13. So theorem 2. In the same spirit of bad grammar, if and only if S is less than or equal to 13, okay, there exists psi belonging to A2 S minus 2 such that the inner product of, so let's do it this way. The integral over H, this H is the whole half plane of F bar, look at that formula over there, F bar is G of Z times the absolute value of psi of Z squared. And now we probably want a Y to the 2p. Sorry, I wouldn't put a lot of money on this number that I'm about to write down. 2p minus 2p plus 2s dx dy over y squared. So I've taken the only change, well, there's two changes with this formula for the Peterson inner product. The first is that most important is that instead of integrating over f, I'm integrating over all of h. The second of the two interesting properties is that I've included psi of z squared, the absolute value of z squared in it. And the third of the two interesting properties is that I've had to add something to this s to make it all work. So the answer is that this is equal to the Peterson inner product. So in other words, there is a holomorphic function whose absolute value is playing the role of the characteristic function of a fundamental domain. Okay, so there's a certain similar flavor between the two conditions. One happens when S... They both hold for 13, yeah. Right, that's sort of corollary, right? But theorem 2.5 is going to be about that, right? What happens when 13 is true? Not only I'll just say it in words, right? Maybe I'm writing it down. For S equal to 13, not only do they both exist, but it's equivalent. Okay? So for S equal to 13, so theorem 2.5, S equal to 13, this property here is equivalent to this property here. And I should perhaps add that this property, when S is equal to 13, should be replaced by these translates actually form an orthonormal basis. So what happens was when S is bigger than 13, they don't span everything, but when S is 13, they're going to automatically span the whole space. Okay, so there's my first 2.5 theorems. So what I claim about these, yes? Is it the same function? It's the same function. One is, it has one property if and only, a function has one property if and only if it has the other property. Okay? So what I claim about these two theorems is that I don't think anyone in the audience who's an expert in either Cusp Forms or Bergman spaces is going to come up to me afterwards and tell me, oh, that's blah, blah, blah. If they do, I will be absolutely delighted because I'm going to try to persuade you that such a function when S is 13 is what I call a holy grail function, that it would really be an amazing thing if you could actually write it down. So the proof that I'm going to sketch later on of the existence of this these psi's, is non-constructive, and it goes via von Neumann algebras. And as far as I can guess, there's no simpler way to prove it. Unfortunately, because of this non-constructive method, all of the things that I like to do with it, I cannot do because I can't write it down. Okay? So now for result 3 of the 3.5. This is one which uses the same kind of proof. The proof is in the same von Neumann spirit, von Neumann dimension spirit. But this one, I think, is relatively speaking easy. And I'll try to, before I even start about telling you what these crazy proofs are about, I'll try to convince you that there's reasons why one might actually be able to answer the question and get the examples. So the question here is obviously write down one of these vectors. Write down one of these analytic functions that has this property. Okay, there'll be part of the question here, but there'll also be other explicit questions. All right, so theorem 3. And this is also has to do with S and 13. So for S greater than 13, not equal to 13, there exists, and for all Z, for all Z, so I take a number bigger than 13, like 14, 13.5, and I take a point in the upper half plane, then what I claim is that I can look at the orbit of this point. Let's let gamma Z equal the orbit of Z under SL2Z. So this is easier to draw, get some idea of what's going on if I draw it in the disk. So suppose Z happened to be 0, then the translates sort of fairly thin around the middle here, but as you get towards the boundary, they tend to get thicker on the ground, and they sort of accumulate towards the boundary, and they have some special points on the boundary where they might do funny things. But anyway, I'm just going to take this orbit, and my assertion is that there exists a psi belonging to the Bergman space A2, S minus 1, S minus 2, which vanishes on this orbit. And of course, this is rather easy. Psi is 0, so let's say psi is not equal to 0. Okay, so that's the third theorem of the 3.5. And I claim that this is probably going to be easier, but maybe I'll just give you a little background. There are some people, you see, who are very interested in these 0 sets of Bergman space functions. And in particular, there's a sort of way, typically this might get left out of the first graduate course in complex analysis. I left it out when I taught it, unfortunately. But if you have a bunch of points in the complex plane, and you want to give a holomorphic function which vanishes at those points, there's this thing called the Blaschke product, where you just force it to vanish. So there's the Blaschke factor, which is like W minus Z over ZW bar minus 1, and some factor, something like W absolute value W over I forget what. This is this Blaschke thing, and if you have a bunch of points like these ones here, and you want to make the function which holomorphic and vanishes at those points, you just take the product of all the Blaschke factors. Okay, so you take the product. In this case, it will be the product over all gamma of W, gamma and whatever is supposed to be in the bottom. Okay, then this is a product which obviously vanishes. The set's obviously holomorphic if it exists. Okay, if it converges. Well, it's known that this thing converges if and only if the sum of 1 minus the absolute value of gamma of w is less than infinity. Infinite products converge if and only if the infinite sum blah 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 converges. Okay, well, unfortunately, it doesn't. Okay, you can sit down and actually try to sum this, do this sum over SL2Z, and you'll find that this actually diverges. So you cannot produce these functions by Blaschke products. In fact, it's known that if you have these, an infinite family of points, the convergence of this sum, the convergence of this product, or the sum as you like, is equivalent to the product that you would get by it being in Hardy space. And Hardy space is a little bit smaller than Bergman space. So this function that we've produced, these functions that have come out of von Neumann magic, are actually in Bergman space, but they're not in Hardy space. So the Hardy space situation is considered very well understood. The Bergman space situation is, from what I can tell, I'm not really an expert, but a bit mysterious. So that's one of the many good questions that are hanging around this this question. And one of the reasons that I think it's a lot simpler, you know, someone's going to write down some definitive answer to this fairly soon. No, I mean, they may have other zeros. I have no way of controlling it. The von Neumann proof that I'm going to give is totally non-constructive. I know nothing about the function except that it's holomorphic. It's in this Bergman space and it vanishes at these points. So apart from that, all bets are off, including, of course, the obvious thing, what happens for s less than or equal to 13? Do they exist? I don't know. Certainly my method of proof does not guarantee it, but it doesn't so far guarantee the opposite like it did for the other questions. There was this clear cutoff between 13 bigger and it was if and only if. This one, I know they exist but for bigger than 13. I don't know what happens for less than 13 or equal to 13.
And they are different for different s?
They're different for different s, yes. Correct. Well, could I swear to that? No, I couldn't swear to that because I know so little about them. But now let me convince you, give you a bit more reason for why I think these functions are this problem is a lot easier. And that is, I'm going to show you how to construct them explicitly. I can now give you explicit examples for s, not for s close to 13, but for s greater than 16. Okay? And what am I going to use? I'm going to use my Cusp forms. Okay? Right? Because there's a little proposition that if f is a Cusp form of weight p, then we can take the multiplication operator by f, multiplication, and that will give us a map from AP, A2 alpha, let's call it, to A2 p plus alpha. This is actually a bounded linear map in Hilbert space. This simply follows from the simple growth estimate of Cusp forms. Okay, so they actually, if you take any Bergman space function, multiply it by Cusp form, you get a Bergman space function, but it's in a higher weighted Bergman space. Okay, but you know, when you multiply, if you take f and you multiply it by some g, then any time f vanishes, this product vanishes, right? And we can easily get functions in Bergman space that don't have any zeros. So you know exactly what the zeros of this f, g are. So using these Cusp forms, you can get elements in A2 p plus alpha vanishing on orbits of the group. Why vanishing on orbits of the group? Well, this is a Cusp form, so it has this invariance under SL2Z, so if it vanishes at one point, it vanishes every other point in the orbit. Okay? It doesn't matter that this one isn't invariant, it doesn't matter. It vanishes because of the first one. And doesn't vanish anywhere else. Okay, so the question is simply, we want to get in p plus, we're going to end up in p plus alpha where p is the weight of the Cusp form. So how small can we make this? Well, obviously 13 is the number we're trying to get. Well, we have delta, right? Delta had weight 12. These spaces start from 1, so we multiply by delta, and we get them explicitly always. Except delta doesn't vanish, okay? So delta is well known to be never 0. Delta of z is not equal to 0 for any z. In fact, that's part of its role in life. It's the denominator in the function for the famous J invariant, which is actually strictly invariant, which is not a cusp form, but delta. So J exists only because delta never vanishes. Okay, so when we multiply by delta, we do get into the right space here if we let alpha be 0, I guess, is it? Or whatever, 1 maybe, I forget. But anyway, we just get in, we just sneak in for bigger than 13, the delta, but we don't get any zeros. So in order to do this, we have to wait until we get a cusp form with zeros. And the smallest value of P for which you get a cusp form with zeros is 16. So for, I guess it works out at being 16 onwards, so the gap between 13 and 16 before we can get, explicit functions. But once you get to 16, you can get explicit functions and say it vanishes at exactly these points. Now, unfortunately, 16 is still not quite good enough because the function that the cusp form of weight 16 is the product of delta and an Eisenstein series, and that Eisenstein series only vanishes at e to the I pi over 3 and its orbits in the fundamental domain. So it's true that at 16, we can get examples vanishing on one single orbit. So that's still an open question. What about the other orbits? Is there a function vanishing on those? Now, if you ramp it up from 16 to 24, then all of a sudden the dimension of the space of cusp forms has got to 2, so you can fiddle with linear combinations and make it vanish at any point, and therefore the orbit of any point. Okay? So there we go. We have explicit examples for much higher weights than we get by this Phenomen method, but explicit examples where we can control everything. So that's why I think this problem is easier than the other two. Okay. So there's my 3.5 theorems. I haven't given you any idea of why they're true. And as far as I know, there's no possible way for the theorems 1, 2, and 2.5 to actually exhibit the functions in the way that we could exhibit these functions here. So of course, as always, I've talked myself out of time. I've got, 10 more minutes, right, Dan? So I'm going to have to give you a slightly impressionistic idea of the proof. But I can't, I'm just going to run out of time and give you no idea of the proof instead. So I have to introduce this Phenomen Dimension, right? That's what this machine is that's going into this. So for that, I want to ask you all the following question. What's the dimension of C plus C? Two complex vectors, right? Well, you think about, well, it's not going to be 2, right? That would be too simple. So you think, okay, I see what he's talking about. The answer is 4 because there's 4 copies of the real numbers. Right? Yeah. Just remember how you got those two answers. The first one is 2 copies of C, so it's dimension 2, 4 copies of R, so it's dimension 4. My answer, much better answer, is equal to 1/2. Okay? Why is that? Well, these C plus C is column vectors, and that's a module over the 2x2 matrices. How many copies are there of the 2x2 matrices in C plus C? Well, exactly 1/2. Right? It's 1/2 a copy. If you take this column vectors and add it to itself, you get to 1. Right? So this is the spirit of Phenomen Dimension. We could ramp this up and do the dimension of C to the n, play the same funny game, and we would get what would be the dimension here. Someone tell me, who's awake? How many columns are there in an n by n matrix? 1 over n, right. Thank you. And you see that as n gets bigger and bigger, we're filling out all, if you took 2 copies of this, you get 2 over n. If you took 3, you get 3 over n. If you took 54, you get 54 over n. So as n ramps up, these numbers are filling out the whole of the real line. And in fact, infinity too, you could add that. So what I'm going to say is a 2-1 factor is an algebraic analytic object due to Murray and von Neumann, which fills the gaps in between these rational functions in exactly the same way that we say to undergraduates, the real numbers fill the gaps in the rational numbers. Okay, so it's a what is it? Well, it's an algebra which has certain completeness properties, completeness properties. And it has the property that, first of all, it likes to act on Hilbert space, so instead of these spaces just being C plus C and C to the n, they're going to be fully fledged infinite dimensional Hilbert spaces. And then there's this number, dimension m of h, which belongs to 0 infinity. And it completely characterizes the Hilbert space as a module over m, just as the dimension of an ordinary vector space characterizes that vector space over a field, right? So this is von Neumann dimension. And it has has a few simple properties that completely characterizes it, and the main one being that the dimension of m is equal to 1. As it should be, 1 copy. Right? All right. So what does this have to do with everything we've been talking about? Well, what I claim is that if you look at SL2Z on Bergman space, A2 S minus 2, if you look at SL2Z on Bergman space, then look at the algebra that it generates and close it, the closure of the algebra generated by SL2Z. Remember, we said right at the beginning, this acts unitarily on this space by fudging the radial-Nikodym derivative of the holomorphic thing. This is a 2-1 factor. It's not actually particularly difficult to see if you go into the theory bit, but there you go, it's a 2-1 factor. So therefore, let's call it M. And what did I say? The only thing I told you about 2-1 factors is that they have this real dimension. So the dimension of M of A2 S minus 2 this is a calculation, and this is where you're going to see this 13 that's been is S minus 1 over 12. So that's where that 13 came in. When S was equal to 13, then what's the dimension? The dimension is 1. What's special about 1? Well, it's right here. That means M is acting on itself by 1. So we've identified the Bergman space for S equal to 13 with the group algebra of SL2Z. Okay? All right, now what about the cusp forms? By the way, this immediately gives us that first result I was talking about. M has the identity, and that has the factor, well, actually, you have to think about it a little bit, but it trivially proves the first one. Cusp forms, well, as I said, we have A2 P, A2 S minus 2, and then A2 S plus P minus 2. I told you that a cusp form is a bounded linear operator from here to here, just by multiplication. And not only is it a bounded linear operator, that's the analysis, it's an SL2Z module map. The property of F of being modular means that this is SL2Z linear. It intertwines the actions of SL2Z. Now, since we're in Hilbert space, every time you have one of these, you have an adjoint going the other way, and that's just as SL2Z linear as the one going that way. So if we take two cusp forms of the same weight, mg star mf, then that's actually in the algebra here that actually commutes with SL2Z. This belongs to, and von Neumann had this wonderful notation for that, M prime. This is the commutant. It simply means that it's SL2Z linear. Now, I'm really down to the wire here with time, so let me just simply finish by saying that one thing I never said about these two unfactors is that they have this trace. There's always a trace, and it's unique. So if you give yourself an element of one of these two unfactors, the first thing you do, right, just take its trace. So we take the trace. You know, it's in that building up the Phenomen Dimension, I started with the n by n matrices and let them get bigger and bigger. Well, the trace is just a trace normalized. So the trace of the identity is 1. So there's nothing terribly mysterious about this. The trace of mg star mf is bounded operators that in this algebra take the trace. This is nothing but the Peterson inner product. And to actually get the full details of that last if and only if theorem, we need the theorem of Radó Lectures, which answered a question that I asked. I said, well, we have every cusp form, every pair of cusp forms gives us one of these operators. Do they actually generate the commutant? Radó Lectures proved, yes, they do, and in a very strong sense, he proved that the linear span of mf, mg star mf, is dense and incommutant. So not only do they generate it, but you don't even have to start multiplying them. Just take the linear combinations of these guys and you've got everything in the commutant. So these results with these results, the theorems that I said, which had nothing to do in their statement with von Neumann algebras, are just trivial corollaries from the theory. So I'll stop there. Thanks.